Okay, so now we are in chapter 4 where we're going to be looking at all kinds of exponential functions as well as logarithmic functions. And we're going to be evaluating them. We're going to be graphing with these functions, and we're also going to be solving equations that contain exponential as well as logarithmic functions. So we start in section 4.1 with the definition of an exponential function, and that would be a function where the base is greater than 0 but not equal to 1. So the base can be 2, it can be 2.5, it can be 3, just as long as it's greater than 0 and not equal to 1. And the exponent can be any real number. Okay, here are some examples of exponential functions. So I said the base is always greater than 0, not equal to 1, and it can be a fraction or a decimal. Okay, and we're going to keep all of the exponents, as we said in this definition, we're going to keep those all as real numbers. So we're not getting into any kind of imaginary exponents in this section. Okay, so using a graphing calculator to evaluate, you're going to want to make sure that you, in some of these problems where they're allowing you to use a graphing utility in MyMathLab, rather than forcing you to do the problem by hand, that you at least know how to handle that calculator in those situations. So, for instance, entering 5 raised to a power of, or to an exponent of square root of 3, when the exponent in and of itself is a new operation, because it's already an exponential problem where you're evaluating 5 raised to an exponent. But the exponent in and of itself is a whole new operation that is evaluating square root of 3. And when that's the case, you're going to want to put a parenthesis around that exponent. Okay, so like for instance, when you're entering this, get out of here, just 5, you can use the caret key, which is right there under the clear button. That'll raise it up to a power, and then you can put your exponent in there. Power, exponent, same thing. So wrap that up in parentheses. Square root is a second function. Call up that square root key. And you know where the square root key is. It's just second function square root. Put the 3 in, close the parenthesis, and then evaluate. Okay, I'm going to round off to the hundredths place, but MyMathLab will tell you specifically where they want you to round off to. Okay, moving into the next problem. In this problem, the power, or the exponent as you can call it, is not actually a new operation in and of itself like it was here, but I'm still going to wrap it in parentheses just because of the negative. You'll actually get the same answer with or without. Okay, so clearing that, 7. Use your little caret key right here under the clear button. Raise it up to a power, and I'm going to put a power of negative 1.6 just as a little reminder. Hopefully you're not still getting error messages because of this. Is negative, you're using this key right here, not the minus key. Okay, so we're going to press in here negative 1.6. I'm going to close that parenthesis, and I'm going to round this one to the hundredths place as well. This will be 0.04. And you can put that leading 0 if you like, or not. Okay, then just a little review of things that will allow you to put expressions in exponential form. So if you have forgotten this, let's just say that you have something in radical form and you want to put in exponential form because you choose to enter it like that rather than as a radical. I'm going to show you how to enter it as both. But let's just say that underneath the radical, you have a base and it has a power of, let's just call the power m, the exponent m. And then you have an index, which is basically names the type of radical that you are taking. And you want to write this radical in power form. Then all you would do is take the base that's underneath, leave that exponent that's attached to it as is, and then we're going to write the exponent in fractional form, just like you see right here. The index would become the denominator of that exponent. here. So here's how, just a reminder of how you can go from radical form into exponential form if you choose to enter it that way in your calculator. Okay, so like an example of that, even though we have another one down here, would be, let's say we have 4 squared underneath. So here's our base of 4. The exponent is 2. And then let's say the index is 3. So you actually have 2 choices here. You can enter it like this. And then you'd have to know where the cube root function is. And you could just put a 16 underneath here. Or you can enter it as 4 squared. Or if you want to go with what I just showed you or reminded you of right here, you could get rid of the radical and write it in just pure exponential form. So the base that you see underneath the radical would stay as is, as would its power. And then we'd go from just a single number in the exponent to a fractional exponent where that index becomes the denominator. So you can enter it either one of these ways. You'll get the same answer either way. So let's practice doing that. Okay, first let's do it using the cube root key. So the cube root is found under the math key. Just come down the first column, hit the math key. You'll notice that one of the functions there is a cube root. So choose that. And you'll have a cube root. And then underneath that cube root, you can either put 4 squared or you can just put 16. 4 squared is 16. Close that up. There's your answer. Now, if this is equivalent to this, then you should get the same answer for both. So let's prove to ourselves that they are in fact equivalent. So now we're going to be entering this as 4 raised up to an exponent of 2/3. Now since this exponent is an operation in and of itself, division, on top of this raising to a power that you're doing, I'm going to enter it like this in my calculator. 4 raised up to a power of 2/3. So 4 raised up to a power of 2 divided by 3. Close that up, and there you go. You see, get the same answer. Okay, here's another example of that sort of thing down below. Only again, you have to be familiar with the keys are. Under the math key, you can actually get any kind of radical. The cube roots are a preset option on the math key. But here I'm telling you exactly the order in which to enter something like this. Again, you could actually evaluate this problem by knowing how to enter 5th root. Or you could enter it in exponential form. You could take that base, raise it up to a power, and the power would be 4/5. You're going from radical to a fractional exponent. And because that exponent implies division, you're going to want to wrap it in parentheses. Okay, so it's up to you which one you want to do, but here's how you can enter either way. First, I'm going to enter it as a radical, so I'm going to clear this out. Okay, now if you're going to use anything that is like where you can't see the index, like when you hit the math key, you can see an index of 3 here. So if you have a cube root, you could use this key, but notice the option underneath it says that the index is x, meaning it can be any value you want, such as what we're attempting to do right now, which is 5th root, and then of course you tell it what's underneath. So if you are going to use this key for option 5, you have to tell it what the x value is first before pressing this option 5 here. So let's quit out of here. Let's first tell it we're doing a 5th root. Then we're going to call up that general root or radical key by just hitting the math and going down to any kind of root. We have already told it it's going to be a 5th root. Press that option. It already knows that the x is the 5 that you've placed out there, and you have to press it in this order. And what we have underneath is an 81. Now, if you don't know that 3 to the 4th is 81, then just press in 3 to the 4th. 3 raised to the 4th. I'm just going to put in 81, so I have to press less keys. And there's your answer. Again, if this is equivalent to this, then you should get the same decimal. So it's 3 raised up to a power of 4 divided by 5. And you see you get the same exact value. Again, I'm going to round it to the hundredths place. I'm going to round that to 2.41. This is the hundredths place. Number next to it makes the decision of whether to round it up or to keep it the same. So 2.41. Whether you press it in as a radical or as an exponential expression. Okay, moving to the next page where we begin graphing. Now, most of this section is graphing. You need to know how to do most of it by hand. You're going to be using your calculator as well, but not to do the whole problem. Now, I've prepared the very first graph for you for myself so that you can see what the shape of the graph is, so that you can see what the asymptotes are, and so you can see the domain and the range. Now, this is what we would sometimes refer to as a parent graph because it does not have any horizontal shifts to the right or to the left. It hasn't been moved up or down, and it has no extra coefficient out here as a multiplier, which would control the width, the stretching, whether that's stretching or shrinking, be vertical or horizontal. That would be taken care of by an extra number. Like, let's say this was multiplied by 5. That would be a vertical stretching that happens there. So what we're going to talk about is just a basic function here where no extra things are happening, no vertical or horizontal shifts, no stretching or shrinking, nothing of that nature is happening here. And so I just want you to get used to what this looks like, how to put you know how to show the work by hand rather than only being able to show us what your calculator can do. I wish I could assign a grade to your calculator, but unfortunately that's not what we're looking for, so you need to know how to do it by hand. You can assist when the problems in my math lab tell you to do so. Okay, so for instance, here's a table, good old-fashioned table that we started to learn to make even back in pre-algebra. We just weren't doing exponential functions then. So we've selected some numbers, trying to keep them as small as possible. You don't need to make your tables this big. I mean, I would probably do a couple negatives, a 0, and then the positive counterparts of whatever you use here. But again, you know, keep these numbers small. So it doesn't need to be quite this big. And if the numbers are going to be too large, I also wouldn't throw those into your table. Okay, so for instance, let's say that you're using this function right here and you're plugging in -3. This would be 2 raised to a power of -3. So please try to recall, how do I rewrite negative exponents? It does not mean that this number is negative. What it means is that all of this is occurring down in the denominator when you rewrite it without the negative exponent. So you bring 2 to the third power, but without the negative, down to the denominator, and you no longer have a negative power. So now it's just 1 over 2 to the third, which is 2 times 2 times 2, which is 1/8. And you can write that as a decimal even. Okay, raised to a power of -2, that would be 2 to the -2. Again, that a negative exponent does not mean the number is negative. It means it gets rewritten like this. It's actually a positive number. It's always 1 over this base raised to this power, but without the negative, all occurring in the denominator. This is really 1 over 4 or 0.25. You can always get the decimal equivalent in your calculator by pressing in numerator divided by denominator. If you press in -1, that would just be 2 to the power of 1, but in the denominator, which is 1/2. Okay, then you get into the easier numbers. They're not negative powers, so they're much easier to calculate in your head. Any base or any real number base to 0 is going to be, we'll be getting with 2 to the 0 we started with here, and we're going to get a 1 for that. So anything to the 0 power is 1 for the kind of bases you're going to be seeing here. Okay, 2 raised to a power of 1, that's going to be 2. 2 raised to a power of 2 is 4. 2 raised to a power of 3 is 8. What I want to try and remind you of is what we have been trying to get across since chapter 2. How do you use a parent graph to create transformations of that graph? I mean, how do we use the values that we have already calculated on the parent graph to help us get all the values for the transformed graph? So in other words, let's say we throw an exponential function at you where you're doing either a horizontal shift or a vertical shift or a combination of the two, or maybe some kind of vertical stretching or shrinking, something of that nature. You can use the values from the parent graph to really get all of the Y partners very quickly, and to even take a look at what's different about the X values without doing a bunch of extra work. This was all heavily detailed in chapter 2, and we just kept doing it in chapter 3 because that's what this class is about. It's about graph theory, how you can get the transformation of one graph from another, and that's what we're going to be looking at in the next few problems. So we have all these values that we already have, like -2 goes with this y part, because you know these are your x's, and then these f of x values, f of x is the same thing as y. These are all the y partners. Okay, I've taken some of the values from this table. As I said, I thought it was kind of large, and I've transferred it to the next graph where I want you to start comparing or being able to compare transformations of the parent graph, which you just saw what it looked like right up here. And let's, before we do go on and compare 3 different graphs, which you're going to be doing in this next example, let's talk about some things that you'll be asked in every single problem: domain, range, and the horizontal asymptote. Notice that a key point on the parent graph, which is kind of a point that we can use to tell what has happened in the transformed graphs, is that it always goes right through 0 if it doesn't have any transformations. So this key point, if we compare this point to what has happened to that point when we're looking at transformations, it's kind of easy to tell what's happening. So here is just the shape of the graph, and I want you to understand that when you're looking at a graph and you want to describe it as increasing or decreasing, you scan the graph moving to the right. So as we move to the right, as we move this way, as we scan this graph to the right, staying right on this graph, notice that the y values are going up, up, up. And this is what we call increasing. So those y values are increasing. And you're going to notice as we take a look at all of the graphs in this section that when you're talking about a base raised to a positive power, the graph is going to be increasing like this. Whereas when we start to get into negative exponents, the graph is going to go the other way, which is what we call decreasing. Okay, just to make sure that you're going to be able to talk about the domain and the range, remember that the domain refers to the x values on the graph. So if you're looking at this graph, notice that the x values go to -infinity out this way. And this leg right here, it looks like it goes straight out, but it actually expands this way. It actually continually expands all the way into -infinity. So for all of these exponential graphs, for all of them, the domain is -infinity to infinity. Even if you flip this across the y-axis or flip it over the x-axis, you're still going to have -infinity to infinity on those x values, because one leg will always flare to -infinity, and one will go to positive infinity. Excuse me, that should be a positive infinity symbol. And one leg will flare out to -infinity. As far as the range goes, well, you have to look and see the asymptote that this exponential graph rests upon. Notice that all these values are very quickly approaching an asymptote, which is the x-axis. There's a name for the x-axis. It is called y is equal to 0. So if we wanted to talk about what is this tail right here, what is it doing? Well, the y values, look, they're very high, the y values, when they're up here. They're getting smaller and smaller and smaller, approaching this boundary line right here. So what is the behavior of this tail end right here? We say that as y approaches 0, and we're approaching 0, see, like that, the y values are getting smaller and smaller and smaller. What is happening to the x values? As y approaches 0, x approaches negative infinity. Okay, and then other things that you want to look at are the range. Now notice that as your graph approaches this line called y equal to 0, which happens to be your horizontal asymptote. You're going to be asked that in every single graphing problem. What is the horizontal asymptote? Well, most of them anyway. So this asymptote is what determines the range. Notice that there's a little discussion of range over here, which are your y values. The range is all about what are the y values. So if this tail is approaching, now I know it's axis, but it doesn't. It hovers slightly above, but so slightly that it's very hard to see with the naked eye. So this is hovering right above this line. It never breaks through this line called y equal to 0, what you know as the x-axis. So this serves as the asymptote. So you always want to identify that line that the exponential function is approaching but is hovering above. So this line right here is your horizontal asymptote. So we say that all the y values on this particular graph, which again is what the range is all about, all the y values are above that 0 line. So they're all greater than 0. If you're trying to give that kind of answer in interval notation, we say that the range values are from 0 to infinity. And I'm going to continue to give those kind of answers or identify those domain, range, and asymptote answers as we go through these problems. All right, so the values that were in this table right here, I've taken most of them and I've put them here. I did not include the -3 or the +2 because you just don't need that many values. I mean, you could actually get away with just -1, 0, and 1, but I'm going to, in most of these cases, I'm going to do 5 values. Okay, so here's your parent graph. Again, these values came from the table above when you put a -2 in there, and I even showed you the work. You don't need to show the work for every single one of these tables, but for the parent graph, it is very wise for you to do it there because the parent graph is more simplistic than any of these other variations that I'm trying to get you to graph. So why do the arithmetic on the harder problems when you can get all the answers for these two tables from this? And that's what I want to stress again. Something that was really stressed in chapters 2 and 3, and we want to continue to talk about how do you get the values from a parent graph to give you the answers for these more convoluted problems. Okay, so using these problems right here, let's just go over how to read the commands of these graphs that are transformed in some way. So notice that this graph, rather than the basic 2 to the positive x, which is this graph right here, I've labeled each one. This goes with this. This is the table of values that goes with this red function right here. So notice that this one has a slight change. It is 2 to the -x. So if you read this command properly, it looks like this says x multiplied by -1. Well, let's try and remember that from chapter 2. And for all the graphs that you're doing, whenever you are being asked to do an operation on x, you will switch that operation. You may remember that when you're doing a horizontal shift, that's a number that's either added or subtracted from x, and we actually perform the operation when we're doing the table opposite operation. So if this says multiply by -1 on the x's, you're really going to divide each value by -1. So I'm going to put that right here, that we're going to divide the x values. I'll just abbreviate here. We're going to divide the x values by -1. And some students will say to me, which x values? The ones from the parent graph. I want you to take the values from the parent graph and do whatever you're being asked to do in this function. Okay, from the parent graph. Now this says only to act differently on your x value than you did over here. Doesn't show you to do anything to the y value. I will point out how you're being indicated to work on the y value. We just haven't come to that yet. Okay, so we're going to divide the x values by -1, and we're going to leave the y values. I meant to put that apostrophe over there, but that's okay. As is. We're going to leave them as is. So look how you do this without doing these calculations all over again. Okay, we're going to take these values, -2, -1, 0, 1, and 2, and we're going to divide each of them by -1, which is only going to cause the sign to switch. So this becomes +2, +1, 0, -1, -2. +2, +1, 0 divided by a negative doesn't change it because it's signless. This becomes a -1, this becomes a -2. Okay, so we've already done the command indicated here that we're going to divide the x values by -1, and we're not supposed to change anything else. We are going to leave those y values as is. So go and grab the y values that went with each of these x values that we just divided by -1. They were 0.25, 0.5, 1, 2, and 4. And you can write these y values as decimals or fractions, whatever you prefer. There are 1, 2, and 4. Now you can even check these. Some students will say, well, how do I know that they're really equal to those things? Well, go and try and plug these in. If you were actually to go through all the work that gets you these answers all over again, rather than knowing how to rely on the work that the answers that you've already gotten from the parent graph, look what would happen. Let's say you weren't sure if you did it right. You could just fall back to that basic skill that you learned when you first made a table of values for the first time. And the way it works is that any x value can be plugged into this function and it should yield the y value. Any of these. If you plug in a 2 right here, it would be 2 to the -2. And look and see that you actually do get a 0.25, even though we got all the answers from the other table. So 2 raised up to a power, if we were to put the 2 right in there, it would be 2 to the -2. And there we go, 0.25. If you were to put a 1 in here, it would be 2 to the -1. 2 raised up to the -1, 0.5. So you see that even if you're going to insist on doing all of these answers all over again by plugging each one of these into the actual function that you're seeing here, you're going to get the same answers as knowing how to change the commands on the new table by using the values that you already did the work for. Okay, let's try it again. We're going to continue talking about that as we go through these tables, transforming to get our new graphs from the parent graph. Okay, let's read the commands here. Notice that the negative is in a different place this time. Instead of it being mingled with the x value, which indicates do something to the x value, it's out here. So what this says is it says multiply your y values by negative. And let me go over that again. When we are working on x's, we will always perform the opposite operation. That is not the case with the y values. So what this is really saying, because of where the negative is it's saying to multiply all your y values by -1. So that's what we're going to do. It is not telling you to do anything to the x values, so you're going to leave the x values as is. Leave those x values just as they are. Again, students will say to me, okay, where should I look so that I can carry out this command and carry out this command? The parent graph. I want you to look at the parent table, where hopefully will be the only table where you're actually working out these values by either pressing them into the calculator or doing them by hand. Okay, so if we're going to do what I just said right here, which is basically what this is saying, I'm just helping you to, review, hey, how do I read those commands? Am I acting on the x or am I acting on the y? So I'm reviewing that with you. Leave those x's as is, -2, -1, 0, 1, 2. -2, -1, 0, 1, and 2. Okay, but on the y's, we said that all we're going to do, instead of plugging each one of these in, putting in the calculator, multiplying it by this negative coefficient, we're not going to do any of that. We're just going to go and grab these y values and we're going to multiply each of them by -1, so that we're not doing any kind of exponential work, not touching our calculator. Just multiplying by -1 just means you just switch the sign. So how easy is that? So take the y partner that went with this value that we switched the sign on and just multiply it by -1. So now it is -0.25. And this would be -0.5 for this one. And this would be value -1. Then the next value was 2. So ours is going to be -2. And that last value was 4. So it's going to be -4. And all of these values are on this blue graph right here. All of these values are on the red graph. And everything that you see in this table is on this green graph. So let's talk about asymptotes, domain, and range again. Okay, on this very first one, we already discussed in the previous graph, because this was the basic parent graph where I talked about this red line is approaching y equal to 0. In other words, the x-axis. So this is the horizontal asymptote right here. Y is equal to 0. That's the horizontal asymptote for this red graph as well as this green graph. Furthermore, the domain and range for both of these exponential functions that are above the x-axis. Okay, so the domain and range for this one, we talked about it in the above problem where this was already graphed. This one we're graphing for the first time, this line that creeps over here to the left. And notice that, again, the domain, which is the x values, this leg right here goes all the way to positive infinity. Whereas the x values on that, don't forget that this spans outward. So this leg goes all the way to negative infinity. So again, on all of these exponential functions, the domain will be on one leg that flares out. It'll go to either negative infinity or positive infinity, and the other one will do the opposite. So domain, negative infinity to infinity. The range, every y value on this green line is above 0. So we say that the y values here go from 0 and above. Okay, I want to talk to you also about the fact that in this first parent graph, I referred to it as increasing, and now I'm going to refer to this graph that I just did the domain and range and asymptote for. I'm going to refer to that one as decreasing. Okay, so this increasing graph is when the power is positive, whereas I'm looking at one that goes this way. So notice that if you're looking at, you always looking at the values on these graphs, you're always scanning it from right to left. So for this graph right here, as we move to the right along the curve, down. That's if we start as far on the right as we can while still being on the graph, and then move to the right. See, I'm moving to the right on the graph, and those y values are going down. So we call this a decreasing graph. Okay, the decreasing nature of the graph means that it came from this kind of exponential graph where the exponent was negative, such as this table that we just talked about. I already talked about the asymptote. Let's talk about this graph that is flipped over. Again, it has an asymptote. The asymptote is the line that the exponential function tries to get dangerously close to. We say in mathematics that the graph is approaching that asymptote. It's getting close to where it almost looks like it's blending right in with the line, but again, it's so close that you really can't see that there is some separation. That line, that asymptote, is still y is equal to 0. That is still the horizontal asymptote here. It's just that since the graph is underneath that line, that changes our range. Okay, so notice that all the y values are less, or in other words, underneath 0. Every single y value on this graph is underneath 0. So it is said that the range is, you know, when you talk about anything in interval notation, you have to talk about the smallest values first, then the bigger values. So it starts at 0, and then all these y values, the y's go to negative infinity. So when I talk about the possibilities for y's, it can go as high as 0, the line y equal to 0, but as low as negative infinity. So there's your range right there. Okay, but absent the asymptote for every single one of these was y is equal to 0, because that's the line that all of them hovered against or approached. As we go into this next page right here, we're going to talk about horizontal and vertical shifts and how they compare to the basic parent graph, f of x is equal to 2 to the x. Just since we're working with that already, let's just keep going with that. Okay, so again, I have transferred the values that go with the basic parent graph right over to this function again, just so you can see, hey, how do I get all the values for these tables right here without actually plugging in each of these x values one at a time and working them in the calculator, because even that's a pain in the neck. So you just have to be able to tell, am I being asked to do something to x, or am I being asked to do something to y, or possibly a combination. Sometimes you can have what's called a vertical shifter, a horizontal shifter, and a multiplicative coefficient, something that multiplies to either shrink or stretch the graph. So again, notice that, look at the position of this positive 3. Do you see how rather than having a 3 mingled up here with the x as it is in this problem, look how distinctly different these look. Here the 3 is added at the end, where here the 3 is mingled with the x. It is part of the x expression. So this is a horizontal shift, whereas this is a vertical shift. With horizontal shifters, we always do the opposite of what's being implied in the function. So where this looks like it's going to be x plus 3, it's presented as x plus 3. The actual maneuver that you will do to get the table is you're going to actually subtract 3. This, on the other hand, is a vertical shift. With vertical shifts, we always do exactly what the function presents. Whereas with horizontal shift, we switch that operation. So we have to continue remembering that as we work through these problems. Okay, so like for instance, let's go with this first one right here where we have a vertical shift. Again, what you're being told to do here is to add 3 to the y value. Since this 3 is not part of the x expression, that means you're using it on the y value. So let's just put a little note here. Add 3 to the y values. And I'll just abbreviate that a little bit. Okay, you're not being told to do anything to the x value. So that means that you're going to leave the x's as is. You're not going to change them. What are we basing these values off of? The parent graph. So when I say leave the x's as is, copy those x's. -2, -1, 0, and 1. I'm just going to go that far. Okay, we're leaving those as is, and then we're adding 3 to the y values. Well, you already have the y values for each of those. So the y value right here was 0.25, and you're adding 3, so it's 3.25. The y value that went with the -1 was 0.5. You're adding 3, so it's 3.5. Yet you're not really doing any of the work of plugging into here, raising to a power, then adding 3. The number that went with 0 was 1, and you're adding 3, so you get 4. The number that went with an x value of 1, so with the 0, there was a y partner of 1, and I took that y partner and added 3. With the x value of 1, here it is right here in the parent graph, the y partner was 2. I'm adding 3, so I get a 5. Okay, add 3 to the y values from the parent graph, from the parent table. Okay, so now I have this graph right here, just so you can get a nice visual on it. I'm going to raise this up just a bit. But here we have the basic parent graph, which is this bluish purple line right here. And then we have this one, and just as you would expect, a vertical shift is what it literally implies. You're raising the entire graph 3 units. So notice that this tail is now hovering right up against a y value of 3. So this is what we refer to a line that graph approaches and gets dangerously close to, but never quite matches up with it. So that also tells us the range. The y values on this green line they're just slightly above 3. So we say that all these y values are greater than 3. So the very lowest this y value can be is just slightly greater than 3, but the y values are going all the way to positive infinity. Okay, and that's where we get this from. But the range is, it's not right on 3. I know it looks like it, so that's why there's an open parenthesis. So it's just greater than 3, but all the way up to infinity. Domain, all the domains are negative infinity to infinity. See, one leg goes to negative infinity with respect to x values, and then the other leg that actually flares out this way, even though it looks like it goes straight up, that goes to positive infinity on your x's. Okay, looking at this next graph. This next graph is with regard to a horizontal shift. And you can tell it's horizontal because the number is mingled with the x expression. So it's telling you to do something with x, but you must remember to switch the operation when you're acting on the horizontal component of the graph. So if it says add 3, you are really going to subtract 3 on those x's. Okay, subtract 3 on these x values. So again, we're just going to look at the x values that are on the table. Now I've only chosen to select 3 values because certain values off of the parent graph are going to give us numbers that are either too big or too small with respect to the numbers that I've placed on this graphing grid. So I'm going to go with, especially since I'm going to be subtracting 3 on the x's. I mean, if I start doing that to this number right here, it's going to be -2 minus 3. I'm going to have -5 for an exponent, and I don't want anything that small. Same thing here. -1 take away 3, I'm going to have -4 for an exponent. So I'm going to stick with these 3 x values, 0, 1, and 2. And I'm going to do exactly what this plan is. So working on the 0 from the parent graph, if I subtract 3, it'll be -3 that I am using for my x value. If I use 1 from the parent table and I subtract 3 from that 1, then my x value is -2. And if I use this 2 from the parent table, but yet I subtract 3, that would give me -1 for my x value. Okay, so I've subtracted 3 from the x's, but I was not told in this particular function to do anything to the y. Otherwise, it would be out here, or it would be a multiplier of that base, a coefficient. And I don't have anything like that. So what that means is to leave the y values as is. So we're going to leave the y values as is. Getting all of this from the parent table. Okay, so I chose these 3 values, this one, and this one, subtracted 3 from each one, just as the gameplay, just as you're indicated that you should do. And then the y values, I'm leaving them as is. So let's see, the y partner that went with this 0 was a 1. The y partner that went with the 1 was a 2. And the y partner that goes with this 2 is a 4. And again, you could always check these. If you're, a little bit leery about whether these calculations are real, check this out. If you put -3 right in there, because you should always be able to check your values this way. -3 right in there, -3 plus 3 is 0. 2 to a power of 0 is 1. Okay, any base to a power of 0 is 1, using the kind of bases we are using in this section. If you were to put -2 in there, -2 plus 3 is 1. 2 to a power of 1, 2. So these things, they all work out. It's just that you are cutting out just almost all the work as you create these brand new tables. Again, on a particular graph, when you compare it visually to the parent graph, again, this purple line was the parent graph. And then what happened in this graph that we just did is there was a horizontal shift. Remember, they behave the opposite of what you're seeing. So when you're seeing a +3, that does not mean the graph is going to shift 3 units to the right where the positives are. Just the opposite of that. It's going to shift 3 units to the left. Okay, and let's compare that. We can kind of eyeball what's going on here. Like for instance, this parent graph went right here through 0, 1. And in the graph where it shifted 3 units to the left, this same point went 1, 2, 3. It just took that point that was right there on the y-axis, that y-intercept, and moved it over 3 places all the way to right here. So this point is what used to be that point. And because that point moved over it, the entire graph moved with it. And so you see all of this coming right through the point and your horizontal shift. That point on the parent graph is a good way to check the shifts that are happening in other graphs, especially when you have all of them on the same set of axes. Okay, moving on. Now let's look at what happens to a graph when the base is between 0 and 1. So a fraction where the top, the numerator, is less than the denominator. Notice that just like when the exponent is negative, it climbs upward and to the left. However, when we're looking at these graphs, we're actually scanning the graph, moving to the right as we do so. We're moving left to right. So always moving left to right and asking ourselves, what's happening to those y values as we move to the right? That's what allows us to give this function or this graph the name of increasing or decreasing. Notice that as you move to the right on this graph, all those y values are decreasing. So we call this a decreasing graph. And I just wanted to point out that your graph will be of a decreasing when the base is a fraction where top is less than the bottom, it'll be decreasing. Or if the base is an integer and the exponent is negative, those also create a decreasing graph with respect to the y value. So again, I have the tables here. I have a table of values. I presented the first one for you. Again, I'm going to look at this as the parent graph because there's nothing being added to x or multiplied by x. No multiplies out here. So this is a nice clean parent graph that we're going to use the values for to get the other graphs that we're going to compare it to. So this is just your basic fractional base where the top is less than the bottom, climbing this way. And I wanted to point out to you how to do these algebraic manipulations by hand because you need to know how to do them by hand. So let's go into plugging in and talking about that. I wrote all the steps for you here. If you were to put -2 right in there, your problem would start off looking like this, 1/2 to a power of -2. But let's remember, what does a negative exponent do to the base? Well, if the base is a fraction, the easiest way to deal with simplifying this by hand is that just simply flipping over the base will change the power from negative to positive. Notice that this has turned into a positive only because this base has flipped over. Okay, so change the sign as you do the reciprocal of the base, and then you'll be into something that you recognize. This is just 2 squared, which is 4. Okay, if you were to plug in -1 into this function, you would put the -1 there. Your problem would start like this, 1/2 raised to a power of -1. As you get that power to go from negative to positive, just flip over through the reciprocal of that base. So it's 2 to the first power, 2. If you put a 0 in there, that's the easy one because anything to the 0 power, based on the numbers we're using in this section, is 1. If you put a 1 as the power, then you don't need to worry about flipping anything over to change the sign because it's already a positive exponent. And we don't need to rewrite those. We just rewrite negative exponents to help us be able to evaluate by hand. Okay, so now this is going to be 0 in here, and that's 1. So when you want to ask me, how do I show the work? That's what I'm showing you in these lecture videos. I'm showing you just how to demonstrate the steps that take you from the more complicated things that you have to evaluate into things that are simpler so that you can do them without the calculator. Okay, 1/2 raised to the power 1 is 1/2. 1/2 raised to a power of 2. Well, you should know that when you're raising a fraction to a power, that you raise the top to the power as well as the bottom. So 1 squared, 1. 2 squared, 4. Okay, don't lose the skills that you gained in the previous class. We have to keep working on those, and being too dependent on your calculator will make you lose the skills. And that's not going to be good in any class, which is all the math classes you're going to be taking here where you have to show your work. So we want to keep working on those skills. Okay, keep going to the next example. And in the next example, I'm going to take that parent graph where the base was a fraction and climbed. It was a decreasing graph, and I'm going to compare it to a graph where I've done a couple of different transformations. Notice in this new graph that I'm also going to place on the same set of axes that I am multiplying the x by -1, and subtracting 3. Again, you have to know what these commands are referring to. Do they want you to change the x, or do they want you to change the y? I mean, the most basic way I can say it is that when they want you to do something to x, the operation will be right here where the x is. If they want you to, if this says x plus 3, you're really going to subtract 3. If this says multiply x by -1, you're really going to do the opposite operation of multiplying by -1, which is to divide by -1. So divide the x values by -1. Okay. And then as far as this -3 goes, that -3 is not mingled with the x in any way. It's out here by itself, so that means that you're going to be performing this on the y values. In fact, this is a vertical shift. Vertical shifting means that it is an operation done on the y values. So on these y values, we're going to be, let's see, I have some room to write it right here. We're going to, remember, you don't reverse the operation when you're doing it to the y's, only to the x's. So even though this appeared as multiplication of the x by -1, we're saying divide by -1, even though you get the same answer when you're working with a -1. So here we're going to subtract 3 from the y values. Okay, here we go. So without recreating all of this work from the previous table, we're just gonna, we read the commands and that cuts out all the work. We were supposed to divide the x values by -1. That doesn't mean anything more than just switch all the signs. So I already did that for you. If you were to switch this, it would be +2, +1, 0, -1, -2. Note that I already put all those in there for you. And I did this on the parent table. That is where these new values came from. Because remember, the parent table had a -2 at the top, and now all of a sudden these are they're all different. They're all switched. And that's because I did this. Okay, now we're going to subtract 3 from the y values. Again, you're doing it to the values on the parent table. So the value that went with this first x value that I switched was a 4, and you're going to be subtracting 3. So 4 take away 3, 1. Okay, then the next value, the 2 that went with this -1 that I switched the sign on, take that y partner and subtract 3. So that will be -1. Okay, then the value that went with the 0 is this 1, this y partner, and we're subtracting 3. So that's going to be -2. And then the next value is 1/2. That's the y partner that went with this 1 that I changed the sign on. So we're going to 1/2, and we're going to subtract 3. And if you don't know how to do that in your head, you could always put it in the calculator. You could just go 1/2 minus 3. You get -2.5. So I'm going to get -2.5. And then that last y partner was 1/4. Remember, you're subtracting 3 on all of the y values. Okay, so these are the answers I've gotten thus far. I'm doing the last one, which was 1/4 minus 3. Again, you can just put it in your calculator if you can't do it in your head. So here's 1/4. You can enter it like that, or you can enter it like this: 1/4 minus 3. So -2.75. Okay, so now I have all these values. What you see in red right here, it's labeled right next to it, is the parent graph when the b value is between 0 and 1. In other words, top number is less than the bottom number. It's the same thing as saying this. The domain flares out from -infinity to +infinity. The range is everything above the 0 line. If which is also considered the x-axis, obviously, but this is the name for it as an equation when we're naming horizontal asymptotes. Okay, so the horizontal asymptote is the equation. You're always going to give it an equation, so you must have an equal sign and the variable y. And then whatever number that tail hovers above. Okay. And now the blue one that had the transformations, notice that all of these go through the table. And again, if you wanted to check these because you're unsure that these are really the values, but if you know how to read the commands properly, just knowing, hey, am I acting on X or Y, you're going to get all these values without any work. If you do want to go and put this sort of thing in here, you could go, but it's a lot of work. You're going to put a 2 right in there, so it would be 1/2, just so you have peace of mind that we're doing this properly. It would be 1/2 to the negative whatever x value you're putting in, we'll put in a 2. Negative exponents get written by flipping over the base and then changing that. That's 4, and then you're supposed to be subtracting 3. Notice that you get a 1, and that's exactly the answer here. So I just cut out all that work just by understanding that when there's a -3 here, that means act on the y values from the parent table in this manner. This x multiplied by -1 means divide all the x's by -1. Remember, we're doing opposite operations when it concerns x, but looking at the values in the parent table. So all I did is look at the x's, divided them all by -1. All I did is look at their corresponding y partners up here, which was 4, 2, 1, 1/2, and 1/4, and I just subtracted 3 from each of those, and I was able to get all of these values, but without any of this kind of work where you're raising to exponents and doing all of that. Okay, notice that because this one has a vertical shift of -3, it takes the parent graph and it drops it down 3 units. Not only that, when you multiply the x by -1, divide all these x's by -1, it takes the graph and look at the way that it was going. It was going like that. Anytime you multiply the x by -1, it's going to take that graph and flip it over the y-axis. We call that a reflection about the y-axis. Same thing as saying it flipped over the y-axis. Okay, so we now have the graph going this way, and it's been taken 3 units down. So instead of having the tail that hovers right above 0, we now have a tail that hovers down at -3. Y is equal to -3. So that tail is hovering right above that line, just as this exponential function was hovering above the line y equal to 0. So this is the new horizontal asymptote now that this graph has been shifted 3 units down. Okay, and there's the wording right there. Okay, domain and range are all the same. The domain is the same, -infinity to +infinity. Same thing for the one that goes like this. The only thing that changes when it's a vertical shift is the horizontal asymptote. Okay, this one I did in the calculator, so you have a little bit of experience doing it both ways. You should know how to control a graph in your calculator if you're asked to use a graphing utility. So here I'm using it to graph the exponential function e to the x and e to the x plus 3 minus 2. If you have forgotten what e is the number, it's an irrational number, just like pi, just like we actually have a square, don't have a perfect root, and it's approximately 2.72. But it actually, it has numbers that go on and on and on. I'm just rounding it off. So, let's see. Okay, and you can see that in the table. See that when you go e to the first power, that would just be e. E to the first power is approximately 2.72. So right here. So I have this as the parent graph, e to the x, and because these are decimals, that's why this one's a good one to do in the calculator. But let's just go over this. If you want to get this graph in the graphing calculator, and you also want to be able to provide me with a table of values, then you need to know how to graph and you need to know how to use the table feature. So let's put the first one in there. Okay, we're going to go to y is equal to, start all over again. Here's the basic parent graph. So that's going to be e. You have to know where to get the e from. You're going to come right down the first column. It's a second function. So press second function right here. And then slide down that column, and right on top of this natural log key, you see an e to the x. So press that. It'll open up for you, and then you put whatever your power was. So for our basic parent graph, it was just x, and you know where to get the x. It's right here under the mode key. Press that x, close up the parentheses. Then for your second function is called e to the x plus 3. Now, since there's more than one term in this exponent, you're going to want to put that in parentheses, but it automatically offers you a parenthesis anyway. And then this is your vertical shifter. This new graph is going to be yanked down 2 units down, and I know this horizontal shift looks like you're going to add to it, almost, for a lot of students. If that means you go 3 to the right, you're actually going 3 to the left. You're doing the opposite, just like you would perform the opposite operation when you go to do a handmade table. Instead of adding 3 on your x's, you would subtract 3. Well, it's the same behavior that goes on in the actual graph. Okay, so let's put the other one in, which is second function. Press that e to the x key. Feed in the exponent, which in this case is x plus 3. Close that up and put that vertical shifter in there of -2. Press enter to make your calculator absorb that function completely. And you can graph using a standard window. So I'm going to go zoom standard. And if I cut off any significant portions of the graph, then I'll adjust manually using the window key. But under the zoom key, you have all these pre-made templates, and I'm going to use the standard window. So enter. Okay, there's one of them, and then there's the other one. So just kind of, and I've already taken a graph that I created online in Desmos, but yours looks the same thing. It is 2 units lower and 3 units to the left. Okay, if you want to see these table of values, all you have, and I wrote out the functions there that you would have to, the strokes that you would need on the table. So when you want table, you just press second table to get the table of values. So like for instance, let's go second. Here's the second key right there. Table is just second command on this graph key. So you go right here. And if you're trying to get all the values for the parent graph, that was the first function. So that would be all these numbers right here. So this is if your x value is -3, that's the y partner. Now we started with -2, so come down here, and you see that it is 1.3534 or 0.135. Yeah, that's the decimals right there, 0.1353. And that is where I got this from. Then you see when x is -1, then it's 0.3679. That is what you see right here. When the x value is 0, then this is the y partner. That's where that one came from, and so forth. Again, since this problem was about different things that you can press on the calculator to get these values, I also got these values from that table. So when you want those values, then you just move over here to the second function. These are all the y values. So we started with -2. On our table, y partner is 0.7183. That's this value that you're seeing here. Then when the x was 1, it was 5.3891 in the calculator. That's this value, and so on. Okay, I'm going to quit out of there, go back to your graphs, and again, let's talk about domain and range. Okay, domain on the parent graph. This red graph, x's go to negative infinity, and on the leg that looks like it goes straight up, but actually flares continuously to the right. So we say that those x's go to positive infinity. So x's go from negative infinity to positive infinity, which is what you see right there, domain. Range. It's all about the horizontal asymptote that lifts up that tail that goes fluttering against the asymptote. That line is called y equal to 0. This is the x-axis, but all y values on this x-axis have a value of 0, and therefore that is the name of that horizontal line. Okay. So the y-asymptote is what you see right there, kind of right on top of it, y equal to 0, but that also determines the range. Everything on this red basic parent graph, those y values are all 0 and above. Every y value on here. And since the range is all about the y values, 0 or greater in interval notation is written like this. Okay, then if we're looking at the altered graph, the one that went 3 to the left and 2 down, there's 2 different shifts going on here. For that, this went how many down? Look at that vertical shift. It went 2 units down. So what you're seeing right here is the tail of this exponential function hovering right at -2, at a depth of -2. So this was the horizontal asymptote for the shifted graph. This was the horizontal asymptote for the basic parent graph, y to y is equal to e to the x. And this was for y is equal to e to the x plus 3 minus 2. Okay, so again, negative infinity to positive infinity, but the range is all these y values are -2 and above. So we say that the y values go as low as -2, but as high as positive infinity. And you know that when you're naming this range, you have to name smaller values first and then finish up with the larger values. So the range on this one, -2 to infinity. Remember, this tail gets very close to -2, but never right on it. So that's why this is a parenthesis around that -2. Okay, there's also, with respect to exponential functions, we have formulas that have exponents in them. So they classify as exponential equations or functions. You can write them in function form. It's not too hard to do. So notice that you're being given these compound interest problems. Here's the exponent right here. You need to know what each of these things stands for so that you can plug into these properly. So when you are trying to earn interest on your money in a bank, you will sometimes, there's different kinds of interest you can be offered. You can be offered compounded interest, and it can compound at different times of the year. So like, for instance, we refer to these things as how often you get interest as the compounding periods. And that's what this N stands for. Let me write that right up here. N is the number of compounding periods. It's how often you get paid interest. So let's say that they tell you that you're going to get paid monthly. So if N stands for the number of compounding periods per year, there are certain words that will indicate to you how often you're going to get paid interest. Let's say that they say you're going to compound semi-annually. Annually would mean once a year. Semi-annually means twice a year. So for the word semi-annually, you're going to put 2 in for N, wherever you see an N, there and there. If they say you're going to get paid quarterly, well, there's 4 quarters in a dollar, there's 4 quarters in a year. So you're going to, actually you get paid every 3 months. But anyway, how many times do you get paid interest? 4. 4 times per year. And again, that is what N stands for, number of compounding periods per year. And in layman's term, it's how often you are paid interest. Okay, and so forth. So if it says compounded monthly, you're going to get paid 12 times a year. So that would mean N is 12. And if you're going to be paid continuously, well, you stop having an N. You no longer have an N, because what does continuously mean? Every second? Every half a second? You just can't, there's no way to count that. So the formula, when you're going to be paid interest continuously, changes from the formula that has N for number of compounding periods to one that does not have the N value. That would be A is equal to P times E raised to a power of R times T. So that's what N stands for. You're also going to need to know what R stands for. Okay, so R, I'll just put that right here. R is the interest rate as a decimal. You have to write it as a decimal. Okay, what else do we have here? Oh, we also have P. So P is the principal amount of money. Principal is just what you start with in your account. And then what else do we have? T, time in years. Okay, so knowing what each of those things stands for, you'll be able to calculate these. So let's say that, I'm going to plug it in over here and then I'll do the answer right here. So we're compounding semi-annually. That means N is equal to 2, the percent, but we're writing it as a decimal, so that's going to be 0.07. And then what else? We also have T equal to 4. And I got that just from the reading of the problem. Okay, we're doing it for 4 years. We're doing it at a rate of 7%, but we need that as a decimal. The N value is 2, and this would be the principal. Okay, principal, time, rate, but as a decimal. And then this word right here gives us what to use for N. So for this first one, it's going to be 15,000. I'm following this formula right here, times 1 plus, oh, I don't think I've given myself enough room here. Let's get this over here. Let me try and do it somewhere else. I want to squeeze all that in there. So let's see if I can do it here. Okay, so this is going to be A is equal to 15,000 times 1 plus R divided by N. R is 0.07 divided by the N, which is 2. And then our exponent is going to be N times T. So N again is 2 times T is 4. So you're going to be putting this in your calculator. Oops, and I think I left one of the zeros off here. Let me fix that. Running out of real estate here. So 15, 1, 2, 3. Okay, so this is going to be 15,000. I'm just going to get one decimal right in here. I'm going to go 0.07 divided by 2 and then add 1. That'll be 1.035. And then I'm going to raise it to a power of 8. Then you can put it in your calculator. Don't put it in the calculator when it still has, so much business to do. I mean, you can if you want to, but I'm going to do 15,000. Oops, let's just go right into the answer. I've simplified it enough. Okay, so here we go. So 15,000, okay, times 1.035 raised up to a power of 8. And you end up with $19,752. You're rounding it off to dollars and cents, so that would be the second number after the decimal place. So that rounds off to 14 cents. 19,752 and 14 cents. Okay, so this is the answer for part A. Okay, here's the answer for part B. Okay, quarterly. I'm not going to do every single one of these, but I'll do part B and part D. So that will be 15,000 times 1 plus R divided by N. So again, the rate is 0.07. The N value this time, well, if you are doing it quarterly, that means that you have 4 compounding periods. So divided by 4, and then we're raising it to a power of N times T, which is again 4 times 4 for the number of years. So just cleaning this up a little bit would be 15,000. And then I'll just get one decimal here with 16 as a power. So this is going to be N.07 divided by 4 plus the 1. So 1.0175. 1.0175, and then you can go ahead and pop that into the calculator once you've cleaned it up to that extent, or sooner if you want. 15,000 times 1.0175 raised up to the 16th power, you end up with 19,798 and 94 cents. Okay, so that is the answer to part B. Here's the answer to part A. So you see you're making more and more interest, or your final amount. This is actually your accumulated amount. So the reason the accumulated amount is higher and higher is because you're making more interest as you get paid more often. Okay, now the best kind, that's the the whole purpose of this exercise that you see. If you're only getting paid twice, you make a certain amount of money. If the number of times you get paid increases from 2 to 4, then that's also going to increase your final amount. So you went from 752 to 792, so it's going up. And if you were going to get paid N equal to 12 times, you would see that you would end up with even more interest in your account above and beyond this 798. Okay, now the highest amount is when, if good luck finding a bank that pays that, good luck finding a bank that pays compounded interest of any sort. But if you were going to get paid continuously, the main point is that for this, the formula switches because you no longer have the ability to tell how often you're going to get paid. So all you know is that it's continuously, so now you're going to be using this formula, which is just principal times E, no n's in here, raised to the rate times time. So this would be 15,000, okay, times E raised up to the rate times the time. Still 4 years. Okay, you might want to get this power first, and then you could put in the calculator 15,000 times E raised up to a power of, you can multiply that in your head or do it in a calculator, of 0.28. Okay, now I'm going to put all of this in the calculator. Okay, so 15,000 times second function E. There's my E, raising it up to a power of 0.28. Okay, and you get highest amount that we have calculated thus far, 19,846 and 95 cents. So again, more often you get paid, the more money you end up with in your account, even though the number of years for each one of these answers is 4. The rate's the same. It's just how often you're getting paid that's changing. And this is the highest amount thus far, the continuous compounding amount. Okay, that takes me to the last problem in section 4.1. which is writing the equation for an exponential function. So first thing is to understand that this graph is an increasing graph. Remember that we use the words increasing and decreasing to identify what's happening with the y values as you scan the graph from left to right. You're moving to the right. So as you're moving this way to the right, what is happening to the y values? Those y values are getting bigger and bigger and bigger. They are increasing. Therefore, this is called an increasing graph. Well, when it comes to exponential functions, increasing graphs were like this. Y is equal to, or f of x is equal to, I guess we should keep things in function form since we're talking functions here, but you know that's the same thing as y. So it's f of x, and this is the kind of function that you're talking about. That's an increasing function. Because if you're using this kind of function where the exponent is negative, it crawls this way, and that's called a decreasing function. So because of the way the graph is, the fact that it is increasing in nature with respect to its y values, I know to use this function right here rather than f of x is equal to b to the negative x. So we're working right off of here. Then I can also mess around with the values that I see on the graph. Like for instance, I see 1, 5, and I also see 0, 1. So if that be the case, well, this graph goes through 1, 5, this plays the role of the x, this plays the role of the y, and I can plug it right in here. Okay, if I'm going to put the 1 in, I have to put it in for x. And I need to put this in for anything that stands for y, which is this f of x is the same thing as y. And then we're going to solve this by not by moving things from side to side, but by observation. Look at what this says. Some number to the first power is 5, and that can only be 5. All right, the only thing raised to the first degree that's equal to 5 is the number 5. So this b value has to be 5. So now when we go to write this function, we have that f of x is equal to, we now know what the base is, 5 to the x. And there, from the picture, we have just written our first exponential function by knowing which function to pick, either the increasing or decreasing function. This is for an increasing function. I could just see it from the direction that it went in. And then I simply just chose one of the points. You could have chosen the 0, 1 if you wanted to. I happened to choose this. You just choose it yourself. And I plugged in this for X and this for Y, and that allowed me to solve for B by observation. Okay, that completes the problems in section 4.1. See you soon for section 4.2.